Okay, wonderful. Thanks, Thomas and Elio, for inviting me to this wonderful meeting. It's great to be here, and this will be an issue that will, to some extent, be closely related in the physics that we're discussing to the first talk of today's session by Andrei Chubukov. So the work itself was done initially with Eliashberg, who when we started working together was a graduate student at Stanford and is now a postdoc at Harvard. And some of the more recent work was done with Konrad Skalm and Jan-Andrej Inkov. Konrad is a field theorist and a string theorist at Leiden. Jan, a student, Veronica, and Davida, also a student and a postdoc, who were involved in the most recent activities here. So the question is very much related to what Andre already pointed out, and it's a problem that has captivated our community for quite some time. Namely, the mere observation that if I go over a number of different systems and I have an ordered state that disappears, let it be in the heavy fermion materials, in one-dimensional charge transfer salts, in the iron-based systems that there seem to be superconductivity largest, right, where there's a quantum critical point. And this is a question worthwhile asking because if I characterize, which we can do in some cases with some acrobatics, the normal state by a non-Fermi liquid state, and for example, describes this non-Fermi liquid state in terms of a singular single particle response. Here by something that's, this is, I think Andre used the letter alpha and said it's smaller than 1, and I have a gamma that's larger than 0. So I have a self-energy that is singular, and I'm not doing something that I'm at least used to do. Namely, I take these singular quasiparticles, I expose them to a pairing interaction. And the pairing interaction is assumed to be instantaneous. So it is just structureless and instantaneous, and then I can do a simple calculation that will at least cause a little bit of a puzzle. Namely, I sum the exact same diagrams that we used to calculate when we look at the BCS instability. And then there's a pairing response of some instantaneous interactions. This pairing response will not be logarithmically divergent anymore. And that's quite to be expected because the objects that are pairing are ill-defined and therefore less singular, less sharply defined, and therefore we get a behavior that reminds us in its nature much more of Stoner ferromagnetism than it is of BCS superconductivity. Namely, we would need a pairing interaction that exceeds a certain critical value. This is a discussion that goes back into the mid to late 90s, and of course motivated by the cuprates. So. And this is worth pointing out because right at the point where we think that we have the largest DCs, it seems to be most complicated to pair. It is not like what we know from the Cooper instability that you always get an instability, but that you have to work quite hard, just like in a ferromagnet, right? And I always point out in this context that there is a paper from Bardeen, who wrote specifically a paper that why sodium is not a superconductor, because you would naturally accept everything to be a superconductor if it's a metal. And there's no paper from Bardeen why sodium is not a ferromagnet. And the reason is clear, because there's a threshold interaction needed and there's no reason to expect that it is. So answers to this type of conundrum were of course given. This is an old question, and answers were given. And there are two different answers, and there are more, of course, in the community, but I give you two answers that I find particularly interesting in this context. One is very much related to what Andre was telling you earlier, superconductivity by critical boson. And the other one is completely different in its nature, at least in its in the formalism, which is holographic superconductivity. So, the superconductivity by critical bosons, we have our fermions. They're coupled to some boson that is in some way or another critical. And then we need to work more or less hard to get our non-Fermi liquid fermion, but that's not enough. At the same time, when you have such a non-Fermi liquid state, you need to pay attention that the interaction is no longer instantaneous, but the same criticality that influence and makes these quasiparticles to be ill-defined also gives you a pairing interaction that is equally singular, and there's actually a relationship between the singularity of the pairing interaction and the non-fermionic nature of the normal state. And that's why you can, to some extent, generalize the reasoning of the Cooper instability, something that goes back to very early work by Boson, and for superconductivity, in color superconductivity of the quark-gluon plasma due to massless gluons, and a very important paper by Abanov, Chubukov, and Finkelstein in 2001, where this issue was pointed out clearly and first to my knowledge. This is one way to answer this problem, and we have seen some comments on it already. There's a completely different way of looking at the same problem, namely pairing of critical systems. This goes back to the formulation by the late Steve Gupser and by Hartnell, Herzog, and Horowitz, who said there is a holographic approach to critical systems where we map a quantum system onto a gravity system in an extra dimension. I give you a couple of comments later, and this at least gives you a framework within which we can formulate the description of critical theories. And within this formalism, we can then do good old-fashioned Ginzburg-Landau theory in this funny curved space. And this Ginzburg-Landau theory then effectively describes to us the pairing of a system that's critical. I never understood a word of this. And that's no disrespect, it's clearly my shortcomings. Sean Hartnell will be here this week, I assume later, and can describe you what motivated them. But I simply did not understand much of this. And partially the motivation for this work was to avoid this flaw. For both of these cases, for both of these very, very different theories, you can complain. We have heard earlier complaints about this one, is there a Migdal theorem, and so forth and so on. And clearly, I mean, what's this all about, this gravity story? And you can clearly hate both of these theories, and then you will keep hating them after this talk. But if you belong to the subset of people who love one of them and hate the other, you will get a problem because they will actually be shown to be identical. So what I want to show to you today is that there's a very deep connection between these very, very different ways of looking at superconductivity in critical systems. A few words on the holographic superconductivity or on the holographic principle in general. We have a quantum field theory that lives in space and that lives in time. And when we then look at this from the side, we can easily add another dimension to the problem. And this additional dimension is where the system experiences its curvature, and it gets interpretation of, say, an RG scale or an energy probe scale that goes from where we typically live to where the low energy theory of the system is located. And this stops typically at a scale that's the order of the inverse temperature. And that's where these holographists usually put a black hole, which makes you stop scaling at this point. So this looks rather obscure to me. I never understood what this here really means for a given many-body system, even though I have, say, some understanding of renormalization group. But then you can do precisely what we discussed. You, for example, look at the Ginzburg-Landau theory in this problem. You write it down. You look at its instability. There's an interesting question. When you get unstable in this curved space, and this is given by an instability criterion worked out in the gravitational literature long ago, so-called Brighton-Lohner-Friedman bound, and then you can study whether or not superconductivity happens in such a curved space. Good. Maybe we skip this. This is just a description of holographic space. So what I want to do today is something that essentially goes back in its spirit to a work done by the late Lev Petrovich Gorkov. So he taught us how, when we started the BCS theory, we can arrive at the Ginzburg-Landau theory in a step-by-step derivation. So if you, of course, are a fan of Ginzburg-Landau theory, this doesn't help you at all because you're already convinced that this is the right theory. If, on the other hand, you want to make a microscopic contact, then this is a very, very useful concept. And what he showed was, of course, what the effective charge was, how he gets, for example, the parameters of the theory from a microscopic calculation, and what the meaning of the order parameter is. And the order parameter is basically determined in terms of the anomalous Green's function of that BCS superconductor. And to remind us what that means, it is an object that depends on space and time points, and which I conveniently can always write in a way that I look at the center of gravity, time and space, and their relative coordinates in a Fourier representation. And if I do so, then of course the center of gravity inhomogeneities, so vortex physics, for example, will be captured by the center of gravity positions, non-equilibrium dynamics by the center of gravity time variables, and the internal structure, for example, D wave versus S wave, or whether I can excite an internally a phonon or not and measure that in an STM experiment, that is given by the relative coordinates. So there are too many coordinates, and that's why I'm reminding you of all of this. Now, what we will be doing is that we start from a microscopic Hamiltonian, something that will have lots of overlap with what Andre talked about, and that we then have an anomalous Green's function in the exact same language, center of gravity and relative coordinates. And from there, we derive and give meaning to this holographic variable, because we can derive step by step. We know what the parameters, what the masses, what the charges of the object are, and then maybe we can exploit some of the ideas that the holographic community has been developing in order to understand critical superconductor. So the model where we start our discussion is so simple that it's almost ridiculously simple. It's the so-called SYK or Kitaev model, where we have fermions that have no kinetic energy, but interacting with a non-local interaction that is even assumed to be random. There's no real reason why this is a good theory for the materials we want to discuss at this point, but let's just move on forward, because what it does is, if you solve this problem by introducing basically collective degrees of freedom that depend on two time variables, something that's very, very common in the disordered quantum spin glass community, for example, then you can get a saddle point where the number of fermions is very, very large, where this becomes exact, and you get a branch cut spectrum for the fermions. So this is the cheapest way to obtain a non-Fermi liquid state that I know of. The non-Fermi liquid solution is a completely natural solution of this equation. That's why it's useful to do this. And when I saw this spectrum for the first time, it was actually a talk given by Dima Bagratz, came from Cologne to talk in Karlsruhe. I asked myself, so what happens when this beast becomes superconducting? And so we want to discuss and answer this question. But there's one more comment that I need to make, because there is already a very close relationship of this simple model, which made it so interesting, and was one of the contributions also by Alexei Kitaev, that the infrared solutions of the system is actually the one that I gave you is actually only one out of infinitely many, and there's a parameterization invariance by which you can generate many, many other solutions that are almost degenerate. And parameterization invariance always reminds you of general relativity, where you can have one coordinate system or yet another one. And the effective theory, low energy theory of these fluctuations is in fact the exact same one that has been developed for de Sitter space or gravitational space in 1+1 dimension. So this was known and was, of course, clearly motivating us when we looked into this issue. So now the model that we looked at is a little bit different, because we needed to make it superconducting. So we used fermions that are non-dispersive and exposed them to Einstein phonons and had the random electron-phonon interaction furnished in a way that so that they get a reasonable large n limit. So you need to, there is some interesting, very closely related work, but there's also extension to finite dimension, which I will briefly mention. So this is not just academic zero-dimensional physics that we are doing here. You can then look at this randomness, and you need to discuss a little bit that you can have, say, configurations that do or that do not break time reversal symmetry, which actually puts us into an interesting situation that we can change the distribution function of these objects to introduce what we call pair breaking. So configurations that would ruin the superconductor configuration that by Anderson's theorem would just untouch at least the superconducting transition temperature. So with all of this, we can copy paste the recipe that the SYK community has given to us. We introduce fields that depend on two time variables. And they, at their saddle point, always look like propagators, Green's functions, or bosons, or fermions, and so forth. But in this system, we also need to introduce objects that are exactly those anomalous Green's functions that Gorkov introduced to us. And if we then do the large n saddle point equation, we get a set of equations that is the exact solution in this limit, and those are the Eliashberg equations. So what we get here is one way to find that Eliashberg equation can be exact in a certain limit. Wonderful. But more interesting is that we can now also solve those equations and ask what actually happens. In the normal state, the answer is very much similar to what I've shown you earlier, branch cut solutions of the fermions. In this specific case, you find, depending on some dimension as parameter that you can introduce, you find at low temperatures branch cut fermion spectrum and boson spectra that at finite temperatures get softened. You get a critical boson mass, so the phonon frequency gets softened and softens as it vanishes at t equals 0. It is a zero-dimensional state, and therefore intrinsically unstable, intrinsically critical, if you wish so. And you find for the normal state fermionic and bosonic objects that they're governed by branch cut singularities with the same exponents that enters there. So there's Landau damping, or fractional Landau damping governs the phonons, and there's non-Fermi liquid behavior of the fermions. Good. All of this is wonderful, and it gives us a normal state where it doesn't even really make sense to distinguish between the fermions and the bosons. It's one soup of a collective degree of freedom that we can at least describe, given the simplicity of the model, analytically. Now we can make it superconducting, and we find it is superconducting, and it has a superconducting transition temperature that in some regions sets in basically when quantum criticality sets in other regions it doesn't, and we can tune the pair breaking parameter to make the superconducting transition temperature arbitrarily small. The main message of this slide is actually very simple. This dependency of how the superconductivity vanishes at this point is something that we have seen in many other contexts of critical systems before, but it's also what superconductivity in these holographic theories have been seeing. So it was clear, it smelled at least like there was hope that we could make connection to this holographic formulation of quantum critical superconductivity. So what makes sense and what helps you to guide yourself is to look at the linearized gap equation. So the one that I think usually is in Andre's talk, and I don't need to talk about it, but I think you didn't even show it today. So it is a linearized gap equation. We see the pairing interaction being singular, or non-Fermi liquid behavior affecting fermions, and we need to solve this equation. You see there's some effective cancellation of powers almost, which is why I call it generalized Cooper instability. Now, if you look at this equation, first of all, as I pointed out, this is something that was discussed. It is from the SYK model. It's the exact linearized equation of the SYK model. But it's also an equation that we know for a long time, namely as the so-called gamma model. There's a large list of potential pairing problems you can study, where this was at least argued to be the right low energy description. Now, if I look at this model, at this integral equation, then you need to find a solution. You can find solutions, but for many of us, it's easier to think in terms of a differential equation rather than an integral equation. I was mentioning this context that there's no command in Mathematica that there's de-integrate equations. There's only de-solve. And that's why differential equations are so much easier. So what you can do is you can take this equation, and at least when this exponent gamma is not too large, you can reformulate it into a second order differential equation. It's easy, it's 5 steps. Everybody can do this very, very quickly. Now, this is the second order differential equation, and it reminded us of something that we had also seen in the context of holographic superconductivity, namely that if you are living in curved space, you can write down the corresponding Klein-Gordon equation of a scalar field in this curved space. And all what we needed to find is what is the proper mapping between our anomalous self-energy of the good old-fashioned Eliashberg theory and the scalar field that lives, or it thinks that it lives, in curved space. And indeed, this is possible. And you can even find here a formulation of, this is the Klein-Gordon equation of a static object with mass m sitting in a curved space of de Sitter space 2 nature. And the entire information about the critical state is actually encoded in the value of the mass of the problem. So this was not the answer quite yet, because it was a static problem and so forth, but it was at least a hint that told us where we could look, and that there was a connection between holographic superconductivity and the gamma model or the quantum critical superconductivity. With a couple of months of more work, we could then figure out how to do this, namely that we have our anomalous grace function, we Fourier transform with respect to relative and absolute time, or maybe only with regard to one of them. It's enough here. Then we need to do a little bit of acrobatics, namely we need to integrate a scalar field over certain geodesics in this de Sitter space. That is not all that important for our discussion, but most important is that we get an interpretation of this additional holographic scale. It is essentially just 1 over the relative frequency that enters the Gorkov function. So it's the Fourier transform of the relative frequency. And the inverse of this is essentially this holographic variable. So with this, we could introduce a scalar field that lives indeed in the right geometry of the system. And when we then rewrite the theory in terms of this new variable, you find, if you confine yourself to the leading Gaussian limit, and we also went beyond this at this point, that this is the action of an holographic superconductor in de Sitter space 2. So the origin of gravity, why are there why there are 2 variables rather than 1, even though it's a 0-dimensional problem, comes from the fact that we have a 2-variable object. We need to look at the Cooper pair as a whole and its internal structure. And these 2 different degrees of freedom give us basically an extra space dimension. This is something we must do in a quantum critical description. We need to look into the Cooper pair and look at its internal structure. One can reproduce where all the individual terms come from, what the value of the masses, these are lengthy equations, but we can microscopically, from a given Hamiltonian, determine the parameters of the theory. It ceases to be a phenomenological theory. It is something that we can derive just like Gorkov could derive the mass or the charges of the parameters. In particular, we see that the absence of quasiparticles gives us a particle-particle response that always gives us a positive mass. In other words, it doesn't want to order. But the pairing interaction being singular gives us a negative contribution to the mass, and they have to balance and fight against one another, and the system has to decide of whether or not it wants to order or not. And in fact, the Eliashberg instability takes place right at this famous Brighton-Friedman bound, where the holographic community already identified the instability of the holographic system. So we have extended this in the meantime also to system in finite dimension. This is a model where we have Dirac fermions that interact with Einstein phonons and couple, have an electron-phonon coupling of a very similar nature. This is something that you will also see in the talk by Premi Chandra on Thursday now, where she talks about polar systems. It's very much the same model. It gives you non-Fermi liquid states, and we find in which channel the system has to condense. This is not important at the moment, but we also find that this problem now goes to an de Sitter ADS4 for a 2-dimensional Dirac system. So the holographic variable now is not the inverse frequency, but it's the inverse Lorentz invariant scale of the problem, of course. But otherwise, we find there's an equivalent holographic information that you can extract for this system, and you can reformulate it again in terms of a gravitational theory. We did the same for a problem with this compressible, with the finite Fermi surface that was discussed by these authors here. And now we get a different geometric description, namely ADS2 cross a flat space, which is nothing else but encoding to us that the self-energy of that system is local. And it's something that the holography community already knew. The charged black holes and actually asymptotically go to a space that is de Sitter 2 plus a flat space. So we have, in each of these cases, we understand why the holographic community obtains certain results. We can, maybe in distinction, however, in addition, maybe we can microscopically determine what these parameters are. At finite temperatures, the mapping again goes in exactly the same way, but now the metric is that of an de Sitter space with a black hole. At finite deviation from charge density, the deviation from half-filling acts like there was an electrical field, which is actually good for superconductivity and enhances the superconducting transition temperatures. All very, very nice details. I'm rushing through this. But we can also do something that wasn't so easy. for the Eliashberg calculation. For example, calculate the entire dynamical susceptibility of that system in the pairing channel. And for this system, you can produce phase diagrams, susceptibilities as function of frequency, and so forth and so on. Look at non-equilibrium dynamics, at least quantities that within an Eliashberg formulation are not quite as easy to obtain and now are completely easy and straightforward to determine within this formalism. So I can conclude that I made two statements here. On the one hand, we have superconductivity by critical bosons, and we have holographic superconductivity. And with a specific toy model and their generalizations to finite dimension, we can connect these two models and know that they are really describing the same physics. The second statement is we determined an explicit map that connects these two, allows us therefore to calculate phase diagrams, calculate dynamic responses, pairing mechanisms, and so forth for systems that have a given Hamiltonian that lead us at least to a critical point, and then we can determine how the collective modes in this holographic superconductor ought to be described. Thank you so much for your attention.